Carbon fiber is one of the most important modern materials ever engineered. Lighter than aluminum, stronger than steel for its weight, and capable of surviving extreme stress in aircraft, race cars, satellites, and high-performance sports gear. Yet the way it's made is far more complex than most people imagine. What looks like a simple black weave is actually the end result of a chemical transformation chain that turns ordinary polymer threads into ultra-strong carbon crystals, then locks them into rigid shapes using precision resins, vacuum systems, and controlled heat. It's a material born from chemistry and perfected by industrial engineering. And today on the How Factory, we're going inside carbon fiber production to see exactly how carbon fiber is made. From thread-like precursor fibers to super strong parts used in the world's toughest machines. The story of carbon fiber begins in the mid-20th century when engineers were searching for a material that could handle aircraft-level stress without the weight of metal. Early carbon fibers were produced from rayon, but performance improved dramatically when manufacturers began using a polymer called PAN, polyacrylonitrile, which remains the most common carbon fiber precursor today. The key breakthrough was discovering that if you heat certain polymer fibers in carefully controlled stages, you can remove everything except carbon atoms, leaving behind long, aligned carbon structures that become incredibly strong. Modern carbon fiber is essentially engineered carbon crystals stretched into thread form, and that's why it's both light and unbelievably stiff. Production begins with the precursor fiber, which looks like ordinary textile thread, but is chemically engineered for the carbon fiber process. Pan precursor is created in chemical plants where acrylonitrile molecules are polymerized into long chains, then dissolved into a thick solution. This solution is pushed through spinnerets, tiny precision nozzles, in a process similar to making synthetic textile fibers. As the liquid jets exit the spinneret, they enter a coagulation bath or air zone, where they solidify into thin filaments. Thousands of filaments are grouped into bundles called tows, and these tows are stretched to align polymer chains, which is critical for final strength. Once spun, the precursor fiber is washed and dried, then wound onto large bobbins. At this point, it still behaves like plastic thread, strong but nowhere near carbon fiber strength. The transformation happens in the next stages, where heat and atmosphere control rewrite the fiber at a molecular level. The goal is to keep fibers perfectly aligned while removing non-carbon atoms in a way that doesn't collapse the structure. The first major stage is stabilization, sometimes called oxidation. Precursor tows are unwound and fed through long heated chambers, usually operating around 200 to 300 degrees Celsius. Unlike later stages, these ovens contain oxygen, and that oxygen is essential. The fiber is heated slowly under tension, so polymer chains cross-link and lock into a stable ladder-like structure. This prevents the fibers from melting when they enter the far hotter furnaces later. Stabilization is one of the longest steps in the entire process, often taking hours, and it's where a huge portion of manufacturing cost comes from. If stabilization is uneven, the entire tow can weaken or break in later stages. After stabilization, fibers turn from white to yellowish brown, and they become stiffer. Now the tow enters carbonization, the stage where the fibers truly become carbon fiber. Carbonization happens in sealed furnaces with no oxygen, often filled with inert gases like nitrogen. Temperatures rise dramatically, typically between 1,000 and 1,500 degrees Celsius. At these extreme temperatures, non-carbon elements like hydrogen, oxygen, and nitrogen are driven out as gases, leaving behind mostly carbon. The fiber shrinks, densifies, and becomes black as carbon structures form and align. For higher performance grades, the fibers may undergo an additional stage called graphitization, where temperatures can exceed 2,000 degrees Celsius. This step further aligns carbon atoms into more crystalline structures, increasing stiffness and heat resistance. Not all carbon fibers are graphitized. It depends on the balance between cost, strength, and stiffness required. Aerospace fibers often undergo more intense processing than consumer-grade fibers. Throughout carbonization and graphitization, tension control is critical. The tow must remain stretched and aligned, If tension drops, fibers develop waviness, weakening the final product. If tension is too high, fibers snap. Advanced production lines use tension sensors, automated rollers, and real-time feedback to keep each toe stable as it moves through furnace zones that can stretch for dozens of meters. When fibers exit high-temperature furnaces, they are nearly pure carbon, but they are not ready for composites yet. Raw carbon fiber has a surface that is too smooth and chemically inert, which makes it difficult for resin to bond strongly. So the next step is surface treatment. Fibers pass through electrochemical baths or gas treatments that slightly roughen the surface and add functional groups. This creates microscopic anchor points, so resin can grip the fiber. Surface treatment must be extremely controlled. Too much weakens the fiber, too little reduces bonding strength. After surface treatment, fibers receive sizing, a thin protective coating applied like a finish. Sizing protects fibers from abrasion during weaving and handling, and it helps compatibility with different resin systems. Different carbon fibers are sized differently depending on whether they'll be used with epoxy, polyester, or other matrix materials. The sized fibers are dried and wound onto large spools ready for shipment or fabric production. Now the fiber itself is complete, but carbon fiber's true power comes when it's turned into composite parts. Carbon fiber alone is like thread, strong in tension but not useful as a rigid structure. To create parts, carbon fiber must be combined with resin, which binds fibers together and transfers loads between them. This is the stage where carbon fiber becomes carbon fiber reinforced polymer, or CFRP, the material used in aerospace and supercars. The first step in composite production is fabric creation. Carbon fiber toes are woven into cloth using looms or stitched into non-woven mats. Some applications use unidirectional sheets where fibers all run in one direction for maximum strength along that axis. The orientation of fibers is critical because carbon fiber is strongest along its length. Engineers design layer directions to handle real-world stresses, stacking layers at different angles to resist twisting, bending, and impact. Many high-end parts use Prepreg, pre-impregnated carbon fiber fabric. In Prepreg production, fabric runs through resin coating machines where epoxy is applied in controlled amounts. The resin is partially cured into a tacky state, allowing it to be laid into molds cleanly. Prepreg is stored cold to prevent curing before use. For part manufacturing, carbon fiber layers are cut and placed into molds. Automated cutting machines ensure accurate shapes and minimize waste. Workers or robots lay layers carefully, aligning fibers in specific directions. This layup stage determines final strength and stiffness. Small errors like wrinkles or trapped air can create weak points. Once layers are placed, the part is consolidated and cured. Many factories use vacuum bagging, where the mold is sealed under a plastic film and air is removed using vacuum pumps. Vacuum compresses layers, removes trapped air, and improves fiber-to-resin ratio. For aerospace-grade parts, curing often happens inside autoclaves, large pressure ovens that apply heat and pressure simultaneously. Autoclaves force resin to flow evenly, eliminate voids, and produce extremely strong parts. Other manufacturing methods exist, including resin transfer molding, where dry carbon fiber is placed in a mold and resin is injected under pressure. This is common in automotive production because it can scale faster than autoclave curing. Regardless of method, curing temperature and time must be controlled precisely to achieve full resin strength without overheating or undercuring. After curing, parts are removed from molds and trimmed. Carbon fiber is hard and abrasive, so cutting requires specialized diamond tools and dust extraction systems. Holes are drilled, edges are machined, and surfaces may be coated with protective clear finishes. High-end parts are inspected for defects using ultrasonic testing or X-ray scanning. Even tiny voids or delamination areas can compromise performance, especially in aerospace components. Quality control is constant from start to finish. Fibers are tested for tensile strength and stiffness. Resin systems are tested for cure performance. Finished parts are weighed, measured, and scanned for structural integrity. Because carbon fiber is often used where failure is catastrophic, inspection standards are extreme. Sustainability is also becoming important. Carbon fiber production is energy intensive, especially during furnace stages. Manufacturers are investing in recycling methods that recover fibers from scrap parts and new precursor chemistries that reduce emissions. While recycled fiber is not always as strong as virgin fiber, it can still be valuable for non-critical applications. What makes carbon fiber manufacturing remarkable is how it turns soft polymer thread into a material capable of surviving aerospace forces. It's not one process, but a chain of transformations. Spinning polymer, stabilizing it with oxygen, carbonizing it in inert furnaces, modifying its surface, then building it into composites with resin and heat. Every step is designed to preserve alignment, because alignment is strength. From chemical plants producing pan precursor to giant furnaces glowing at thousands of degrees, from woven sheets to pressure-cured parts inside autoclaves, carbon fiber is a modern manufacturing masterpiece that blends chemistry, heat, tension control, and structural engineering into one of the strongest materials ever made. And that is exactly how carbon fiber is spun, stabilized, carbonized, surface-treated, sized, woven, molded, cured, and inspected, transforming simple threads into super strong parts that power aircraft, race cars, and next-generation technology. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the materials, machines, and factories behind the world's toughest products.